Okay, so we are starting the last couple sections of the chapter. That means the chapter test will be coming up here shortly. So let's get started. We got section 1.7, which is the chain rule. And we're going to talk about just a specific part of the chain rule. But the chain rule applies when I have what's called a composed function or composition of functions. This is a composed function. So if I had something that looked like this, to put numbers in it for you, x cubed plus 9x, and that whole thing was raised to the 6th power. Okay, that is a composed function. It is composed of two functions, f of x, which is x to the 6th, and g of x, let's just write them this way, f of x, which was x to the 6th, and g of x, which is x cubed plus 9x. Okay, so that means we plugged the g of x function into the x in f of x. We composed the function. All right. So when we are taking the derivative of a composition, we're going to take the derivative of the outside. That means we're just going to work with the outside. We're going to leave this inside part alone. Don't do anything with it, just do the outside. But then we have to multiply that by the derivative of the inside. All right. So let's look at how that works. We're going to do what's called the extended power rule for ours, which means the derivative of the outside, so this is your derivative of the outside, is going to use the power rule. So we're going to bring that power out front, subtract 1, leave this inside alone, but then we're going to have to multiply it by the derivative of the inside. So let's look at an example. So if we have this example, okay, this is our composed function. The derivative of the outside looks like this, 1/2, right? I took that exponent and I brought it out in front. 1 plus x cubed. Notice I did not change anything here. This is exactly as it appears here. Subtract 1, so it's a negative 1/2, times. Now I have to take the derivative of this inside part. So the derivative of 1 is 0, and the derivative of x cubed is 3x squared. Okay, so that is the chain rule. I do need to multiply the things I can multiply together. I can't do anything with this because it's raised to the negative 1/2 power, but I can combine this and the 3x squared. So I'm going to get 3x squared over 2. I'm just going to multiply those two things. Remember, anytime it's a whole number, there's a implied 1 on the bottom, times 1 plus x cubed to the negative 1/2. Okay, so that, I will accept that as your final answer. If you want to fix that negative 1/2 exponent and put it in the bottom as a radical, that's fine too, but you do not have to do that. All right, I want to look at another example. So here's another example, this one with a whole number. Go ahead and pause the video so you can try it. So let's call this f of x. So f prime, our derivative of this function, is going to be the derivative of the outside, so 7. Leave this part inside the parentheses alone, don't change it at all, to the 6th, times. Now I have to take just the derivative of this, so that's going to be 3x squared minus 5. Okay, again, I have to combine the parts I can combine. I can't do anything with this one. I can't get inside those parentheses because of that 6. So unless I want to multiply that thing out 6 times, which I don't, we can't do anything with that. But we can multiply this and that. So 7 times 3x squared is 21x squared, and 7 times 5 is 35. Make sure you put parentheses around that, because those two are going to multiply by all of this, so we have to make sure that that's clear. That's why we're using those parentheses. Okay, so that would be your final answer. All right, we are going to combine two rules here. So we're going to find the derivative of this using both the product rule and the extended power rule or chain rule. Okay, so we're going to do two rules. This is a product. Okay, so let's do it this way. Let's call this g of x, and let's call this h of x. Okay, so we'll make a curly Q there. All right, so let's go ahead and say g of x equals 3x minus 5 to the fourth. G prime, remember we need G prime, H prime to do our product rule. So G prime is going to be 4, leave the inside alone, cubed times the derivative of the inside, which is 3. So G prime is going to be 12 times 3x minus 5 cubed. Okay, h of x is 7 minus x to the 10th, and h prime of x will be 10 times 7 minus x to the 9th times negative 1. Okay, so all that's going to do is make this negative 10 times 7 minus x to the 9th. Okay, so there's your h prime. All right, so the four things we have, let's go ahead. We're going to highlight those. So we have G prime, H prime. And let's go ahead. So we used the power rule, the extended power rule, to get both our G prime and our H prime. Now let's put all that together in our product rule. So product rule says first leave it alone, so that's our G. So we have 3x minus 5 to the fourth. First leave it alone. Times the derivative of the second. Well, that's our negative 10 times 7 minus x to the 9th, plus the second, leave it alone, 7 minus x to the 10th, times the derivative of the first, which is 12 minus, times 3x minus 5 cubed. Okay, and there's not a lot we can do there unless you want to factor things out, which doesn't actually make it a lot neater, so I'm not going to worry about that. You can leave that as your final answer. All right, on to section 1.8, higher order derivatives. So the idea here is, so we already know how to take the derivative of this. We have this function, take the derivative. So the derivative is 5x to the fourth minus 12x plus 1. Okay, that's our first derivative. The idea with higher order derivatives is that we can take the derivative of a derivative. And I will talk in a little while about why that is useful, but I can find out how my rate of change is changing. Okay, so we have some notation. So let's talk about it this way. If we have y as our original function, we would have y prime as our derivative. Our second derivative is y double prime, y triple prime, y fourth, or you can change it to a 4. Okay, so we would have f prime, f double prime. Okay, f double prime is the derivative of f prime, f triple prime. The other way you're going to see this is, maybe that's on the next screen. Okay, so that's just the third, fourth, and fifth derivatives of that function. Okay, so if this is your original function, f prime of x is 5x to the fourth minus 12x cubed plus 1. Your second derivative of double prime is 20x to the third minus 36 6x squared. Your third derivative is 60. Now remember, your third derivative means I'm taking the derivative of this. Let me rewrite that because it's messy. So that was 20x cubed minus 36x squared. Okay, so my third derivative is 3 times 20. That would give me 60x squared minus 72x. My fourth derivative is going to be 120x minus 72. My fifth derivative is 120. My sixth derivative is 0, and every derivative after that is 0. Now remember, derivative being 0 means the slope is 0. That does not mean that it doesn't exist. 0 and does not exist are not the same thing. It very definitely exists, and any derivative past 6, the derivative would be 0. So I want you to look back at our original function and look at our exponent on our leading term, meaning our largest exponent in that function, and look at where the last derivative is that has a number other than 0. Okay, those match up. So when you are doing power rule higher order derivatives, this only works for power rule of positive exponents, you will notice that if the derivative you are asked to take is bigger than the exponent you started with, you don't need to do all this work in between. You can go straight to the derivative being 0. Again, I want to stress derivative equals 0. That is a number. That does not mean it doesn't exist. It very definitely does exist. A seventh derivative would exist and would also be 0 for this function. All right. Here is what I was trying to get to. That Leibniz notation, we had dy dx when we were just taking derivatives. Now when we take a second derivative, we get d2y over dx2, which is read the second derivative of y with respect to x. And we can keep going with that. d3y over dx3, that's the third derivative. d4y over dx4, that's a fourth derivative. Whatever the number is here and here, that has to match, and whatever that number is the derivative they want you to take. So if it was a 6, they would want a sixth derivative. All right, so this says take a fourth derivative of this function. So y prime. So y prime is going to be 35 x to the 6th minus 10x to the 4th plus 16x cubed plus 18x squared. Remember, if you want to do this on your own before you see the answers, go ahead and pause the video. Y double prime, and I'm going to throw that in my calculator so I don't mess it up. 35 times 6. So I have 210x to the 5th minus 40x cubed plus 48x squared plus 36. Y triple prime is 1050x to the 4th minus 120x squared plus 96x, and the fourth derivative is 4200x cubed, that one should look like a 4, sorry, minus 240x plus, that should have been an x, I'm so sorry, that should have been a plus 36, plus 96. I just left that guy right off. All right, so this should be your final answer. All right, let's try one more. This one just wants a second derivative, so that should be easy enough. But we don't want to do this if we don't have to. I do not want to do the quotient rule twice if I don't have to. This is a fraction, but I would prefer not to. So let's think of an easier way to do this. What if I rewrite this as x to the negative 1. Remember, it has a 1. It's in the bottom. If I move it to the top, it just makes that exponent negative. Okay, then my y prime becomes negative 1x to the negative 2. And y double prime, negative 2 times negative 1 is a positive 2x to the negative 3. And you can leave it like that. Okay, and we could keep going if we wanted more derivatives on that. So the easiest way to do those is not to try to do a quotient rule, but to rewrite it in this format so we can just do a power rule. All right, now we have a chain rule that we want to take the second derivative of. Remember, there's no shortcut on these. We've got to take the first derivative in order to get to the second derivative. So y prime equals 20. Remember, we're taking the derivative of the outside. X squared plus 10x to the 19 times. Now we've got to take the derivative of the inside, which is going to be 2x plus 10. Okay, and then I want to multiply the 20 and the 2x plus 10 together. So my y, actually, let's just leave it here. So this actually equals 40x plus 200, put that all in parentheses, times x squared plus 10x to the 19th. Okay, that's my first derivative. Okay, you need to simplify. Simplifying is not taking another derivative. Now we can take the derivative of that. All right. This now is a product. I am multiplying two things together. So in order to do this one, in fact, let's go down here. Let's call this one f of x and this one g of x. I can make a little list here. So f of x is 40x plus 200. F prime of x is going to be 40. G of x is going to be x squared plus 10x to the 19th power. And G prime of x will be 19x squared plus 10x to the 18th power times 2x plus 10. Again, we're going to need to simplify that down. So that's going to be 38x plus 190. Okay, so this is all g prime of x times x squared plus 10x to the 8. Okay, so we just simplified all of that. All right. So using the product rule, the first, well, that's right there. So the first is 40x plus 200 times the derivative of the second. Well, that's 38x plus 190 times x squared plus 10x to the 19th. Okay, just moving down to the next line because I don't have room up there. Plus the second, which is x squared plus 10x times 19 times the derivative of the first, which is 40. All right. The only things here we could combine are those. So we will go ahead and do that. We can multiply those two out. So that would be horrible numbers. So we have 40 times 38. So we have 1520 x squared. And then I'm going to have 40 times 190. So that's 7,600. I'm going to jot that down over here because I know I'm going to have to add it with the next term, 7,600 x's, but I'm also going to have 200 times 38. Which is another 7,600. Okay, so I ended up with 15200x plus 3,800. Okay, so that's what happened when I multiplied those two together. Actually, let's not call that y prime, double prime right now. Let's go ahead. We're going to extend the page a little. Okay, so we're going to have my y double prime is going to equal 1520 x squared plus 15,000x plus 3,800 times x squared plus 10x to the 19th power plus, sorry, that should have been 8, plus x squared plus 10x to the 19th times 40, and I'm going to throw the 40 out in front. That would be your final answer. That's a little messy. No, I would not give you one quite that complex on a test. But that would be how you would multiply that all out. All right, here are a few that you can do on your own if you would like. These are all just asking for a second derivative. So on this first one, y prime, let's get our first derivative. It's going to be negative 24x cubed plus 6x. That means y double prime is going to be negative 72x squared plus 6. On this one, we want to rewrite before we start, so we're going to have 2x to the negative 3, which means y prime equals negative 6x to the negative 4, and y double prime equals 24x to the negative 5. On the third one, we have a chain rule. So you know what, we're going to skip that one this time because we don't want to keep doing chain rules, second derivatives of them, since we just did an incredibly difficult one. And this last one, remember, this equals, so y equals x to the negative 1, which means y prime is negative 1x to the negative 2. Y double prime is 2x to the negative 3. Y triple prime is negative 6x to the negative 4. And y to the fourth is 24x to the negative 5th. Okay, so that is how those work. All right. All right, so here's where we can give a little more meaning so we can understand one idea of what higher order derivatives give us. Okay, so if we call okay, so remember our velocity is a first derivative, right? If we start with a position function, s of t, our velocity would be s prime. Okay, when the policeman stopped us, we were 90 miles away from KSU, but we were also going a specific speed at that moment in time. Okay, so that's our velocity. And yes, it would be the limit of s t plus a, the whole simplified difference quotient. But we don't have to worry about that because we have some easier patterns that we can use instead of having to always do the difference quotient for this. All right. But as we are going a specific velocity, when I see the policeman, what is my gut reaction? Probably I hit the brakes, which means I am trying to change my velocity, right? I am negatively accelerating, decelerating, right? Because I hit the brakes. So the speed at which I was traveling, my velocity that I was going, is changing. Okay, and that's my acceleration. So acceleration is how my velocity changes, or the second derivative of my position function. Okay, there is also a third derivative. It is called the jerk. So when you are accelerating and then you decelerate, right? You changed how you were accelerating. That is called the jerk. That is a first derivative of acceleration, a second derivative of velocity, but more importantly, it is the third derivative of my position function, and s of t is my position function. Okay, so that's one of the things that gives meaning to all of these higher order derivatives. Okay, so here we have an example. My position function is given by s of t equals 10t squared. I want to find the velocity function. Well, that means take the derivative of s of t. So 10t squared, my derivative is going to be 20t. And then find my acceleration function. Well, that's going to be the derivative of velocity. So the derivative of 20t is just 20. Okay, then they want us to find the distance, the velocity, and the acceleration when we've traveled for 4 hours. Okay, so if I plug in 4 hours into each of those functions, so 10 times 4 squared, I am 160 miles away from where I started. My velocity, I have to put that into this 20t, so 20 times 4 means I'm going at that moment 80 miles per hour. And my acceleration, well, that doesn't have a variable in it, so I am accelerating at 20 miles per hour squared. Okay, now this acceleration of 20 being constant, probably not very likely, but that's what this one is saying. That's my acceleration. And evidently it is constant and not changing, so there is no jerk in this particular example. All right, so hopefully that gave you a little meaning to why we do the higher order derivatives. We can see how something else is changing, how our first derivative is changing, how our second derivative is changing.